Let's break down the ELBO for VAEs. It's ELBO equal to E log P x given z minus KL Q z given x and P given P of z. So the likelihood term log P of x given z how well we it tells that how well we reconstruct the data, and KL terms is that how close our latent space is to the normal standard. For diffusion models, ELBO appears differently, measures how well we reverse the noise process. Each step has its own KL term comparing to the forward process. And why it matters? The VAEs balances reconstruction versus organized latent spaces. Diffusion controls the noise removal precision, and ELBO is the secret sauce for both models. And that's all about the ELBOs. So coming to the second question, which is about deriving and explaining the structure and the meaning of a β-VAE objective. So basically, for that we'll have to crack down what is β-VAE's objective. Equation involves E log P x given z minus beta of KL Q z given x, which has P of z. And this is a tweak to standard VAs, which adds to a beta coefficient to the KL term. And first we need to understand what beta controls. So beta, in the case when beta is greater than 1, then it forces stricter Gaussian latent space, which for better disentanglement, and when beta is less than 1, then it prioritizes the reconstruction over structure. And when beta is equal to 1, that means it's a standard VAE. So coming to that, let's see how the beta changes representation. When the beta value is high, then latent units snap to axis aligned features, and when the beta value is low, then it is like mixed but accurate reconstructions. Beta VA's superpower control trade-offs between learning dependent factors and preserving details. Thank you. So let's understand first our question, that how do diffusion models create stunning images from noise. So let's break it down here. Like, diffusion models work in two phases. One is forward process and reverse process. In case of forward process, they gradually curve the data with Gaussian noise over time steps, like blurring a video until it's pure static. And the reverse process is a neural network learns to undo this noise step by step, recovering the original data distribution. The magic lies in the reverse translation. At each step, the model predicts and removes noise using a learned mean, which is mu, and a variance. The training minimizes the KL divergence between forward and reverse paths, forcing the network to master denoising. By learning to reverse diffusion, the model extracts pattern from noise. Sampling starts with random noise and iteratively refines it into coherent data. That's diffusion in 60 seconds. So let's break down the Gaussian VAE loss in 60 seconds. The ELBO loss has two key parts. Reconstruction loss, that is E log P of x given z, which measures how well we rebuild input x from latent z. For Gaussian input outputs, this becomes MSE, and for Bernoulli outputs, it's cross entropy. KL divergence, KLQ, where z given x is parallel to P of z, forces our encoders P z of x to match the prior P of z, which is equal to n0, I, has closed form solution for Gaussians. And the reparameterization trick, which is instead of sampling z similar to q z given x, we write z equal to mu plus sigma into epsilon, where epsilon is similar to n0, I. This lets gradients flow through mu and sigma during backpropagation. Together, these components enable the stable training of deep generative models. So, coming to the fifth question, which is about the research papers we learned throughout the course, It is like in 2025, the generative AI isn't just trending, it's transforming industries. So here's why mastering GANs, VAEs, diffusion models, and transformers is a game changer. So GANs learn to create hyper-realistic images and videos. Think of deepfakes, art, or ads. Use them in a project to augment medical imaging data. And VAEs understand probabilistic modeling for anomaly detection, crucially for cybersecurity and healthcare. The diffusion models mastering state-of-the-art image generation like DAL built a custom logo generator. Transformers NLP's backbone like ChatGPT, Gemini, fine-tuned one for a customer service chatbot. And why it matters that these tools helps to innovate across fields from AI art to life-saving diagnostics. Next, combining them diffusion plus transformation, which can be used for video generation. Thank you. So in spring 2025, the learning GNs, VAs, diffusion models, and transformers have been a game changer for me. These models are shaping the future of AI, and this course didn't just cover theory, it gave us real world coding experience and deep insights into how these things work practically instead of just reading in theory. So through assignments, we built AI and diffusion models from scratch, trained GNs, and saw firsthand the challenges like mode collapse and evaluation metrics like FT. Working with transformers helped me understand the architecture behind powerful tools like BERT and ChatGPT. From a career perspective, this knowledge is incredibly valuable. Employers are actively looking for people who can apply generative AIs to real problems, whether it's in vision, NLP, or healthcare. Understanding these models gives me a competitive edge in both industry and research roles. Overall, this course helped me build a strong portfolio, improve my AI intuition, and get one step closer to working on impactful production level generative systems.